Okay, all right. Welcome everyone to yet another event from our Geography Awareness Week. I am Mariana Pavlovskaya. I'm chair of Department of Geography and Environmental Science. And as you know, during this week, we make an extra effort to make it known to the world how important geographic knowledge is, especially in the times like ours, right? At the times of climate emergency, at the time of growing and tragically at times deepening social and economic inequality. And it is geographers that think about how different parts of the world are connected, how different places are connected, and also how nature and social relations are connected to each other. And during this week, we have several events that illustrate different dimensions of those processes. On Monday, for example, we had an amazing lecture by Dr. Celeste Winston about geographies of Black worlds of freedom. And there she was talking about what she called fugitive infrastructures. So today we have Professor Charles Vörösmarty, and he will be introduced in a minute, who will be talking about water infrastructures. So it is interesting how very, very different phenomena, very different processes share a certain language and enable us to understand those phenomena in themselves, but also to kind of sense their connections. So I would like to thank Amy Ju for supporting all our events this week. I would like to invite you to yet another event, which will be tomorrow. This is a panel, I think it is called Panel on Climate Emergency, organized by our students. So please make sure you attend that one as well. And right now, I would like to introduce Indy Ryman, who is an assistant professor in our department specializing in environmental science, who will be introducing Dr. Charles Vörösmarty, who will give a lecture tonight. Welcome, Indy.
Thank you, Mariana. It is a real pleasure and an honor to have the opportunity to introduce Dr. Versmarty. He's had an incredibly impressive career, and so what was difficult is to try and figure out how to succinctly introduce him in just a few minutes. You'll hear a lot about his great work, so I won't go too much into the details there, but Dr. Versmarty is the founding director of the Environmental Sciences Initiative at the CUNY Advanced Science Research Center, and is also a professor of civil engineering at City College of New York. He got his bachelor's degree at Cornell University and his master's and PhD degrees from University of New Hampshire. He's a global expert in hydrology and water resource systems. And more broadly, he is just an incredible big thinker in various fields of environmental science and really a leader in interdisciplinary and convergence style research. His research focuses on development of computer models and geospatial data sets used in the synthesis studies and the interactions of among the water cycle, climate, biogeochemistry, and anthropogenic activities. His work is built around local, regional, and global modeling of water balance, discharge, constituent fluxes in river systems, and analysis of the impacts of large-scale water engineering on the water cycle. His work has been, and I'm sure will continue to be, incredibly influential. He's published more than 200 scientific manuscripts and has contributed to more than 30 books. Collectively, his work has been cited more than 50,000 times. Did I mention that he's an incredibly influential scientist? He routinely provides scientific guidance to US and international water consortia, as well as the UN, and he was appointed to the Arctic Research Commission by Presidents Bush and Obama. The list goes on and on, but I will cut it a little bit short there. And I'll also add that he's spearheading really exciting efforts to develop global scale indicators of water stress. I've had the good fortune of knowing Dr. Versmarty for 4 years now. He's a big part of the reason why I came to CUNY, and I can say knowing him for 4 years and having him as a mentor as I'm sort of developing as a scientist, I can say that he is not only a highly influential scientist, but he's just a really wonderful person and mentor. So I will hand it over to you, Dr. Versmarty, and I will just also ask everyone to save your questions until after the presentation. But if you have any clarifying questions, feel free to post them to the chat window during the presentation. Thank you, and it's really exciting to have you here.
Oh, so we got a question. You're on.
Sorry?
You're on mute, Charlie. Sorry.
I think I'm unmuted now. Was that the question? Was that? Okay. Thanks so much for that very nice introduction, Andy. I'm getting choked up here, so I hope I can get through this talk here. Let me share my screen, and I'm going to hit my first slide here. Can everyone see that first slide? Okay, so what I'll be talking about, as Mariana mentions, is infrastructure. And I think you probably gleaned from the introduction that one of my arenas of interest is water. And in fact, I would consider myself a hydrologist, I guess an earth system scientist type of hydrologist. So I come from the physical angle of things, but I've had the great fortune over the years to work with people who have really broadened my vision of the importance of biology, of chemistry, and of human dimension issues relating to water. So what I'd like to do today is to talk about what I view as a capstone effort of something called the Global Water System Project that ended a few years ago, but it was a decade-long project, and I was a co-chair of a committee that brought together literally hundreds of scientists to talk about new ways in which we could view the global water cycle. And one of the, I think the hallmarks of that effort is that we convinced the scientific community that looking at things at the broadest of scales, at the global scale, was in fact a legitimate subdiscipline of hydrology, although that did take some some convincing and some nasty intellectual fights over the years, but I think we finally prevailed in getting people to understand the importance of that broad scale. So what I'm going to talk about now is some work that we did toward the end of that Global Water System Project effort, looking at how nature-based contributions in tandem with engineered infrastructure could bring about better water security. And I'm sure that most of the people in the room here understand that water in the 21st century is a very important strategic resource and often spoken about in crisis terms, in particular becoming much more concern under the climate change issue. So what I like to do is I'd like to summarize that work. This involved about a dozen other technical collaborators. So there's a lot to this, but I'll try to summarize it as best I can. And I'd like to end the discussion with maybe some points of, let's say, grand challenges in hydrology that I think will keep us occupied as a community for the next many years. So let me go on to the next slide, and please tell me if you either cannot hear me, if I'm not making sense, or if you can't see the screen. I guess what I'd like to begin with here is just an introduction to my home institution, as is Andy Reinman's, along with Hunter College for Andy, and for me, City College. That's where my academic appointment is. We came together about 5 years ago as a team here. Gillian Small, if you know, was the vice chancellor during what we know at CUNY to be the Decade of Science, which ended in 2015. And one of the important hallmarks of that effort was to invest in science and facilities that are encapsulated within this building. So there are 5 different floors to this building. Andy and I sit on the top floor in environmental science. And our brethren are in neuroscience, structural biology, photonics, and nanosciences. What's interesting about this building is first of all, it's meant to draw in constituencies, that is faculty, staff, and students from around the other 24 campuses, okay? And our day jobs are to try to catalyze CUNY-wide research in these domains. That's part of the directive that we received from Jillian back in the day. And we broke ground, I guess, around 2010 or so, and by 2014 we were open for business. She also told us that it was important to cross-fertilize up and down the floors, because she really envisioned this as an interdisciplinary institution that could have people who do environmental science talk to people who do nano research. And I'm having trouble advancing my slide, but there we go. So one of the interesting aspects of the effort encapsulated by the building here is that we work across many, many different scales. And Andy and I work on Earth systems and the environment, and our characteristic length scale are in hundreds, thousands of meters, okay? And those who work down at the level of nanoscience or structural biology that are positioned within the building, they're talking about 10 to the minus 9th meters. And miraculously, we can actually talk across the scales. And one of the interesting aspects of this diagram we noticed when we brought it together was that the midpoint, at least in logarithmic scale, is the human being. And sure enough, a lot of the research that's going on in the building is dedicated to improving the lot of humans. There are people who work on, for example, innovative chemical delivery modalities for cancer research or in cancer research and for finding cures to cancer. We have people who are looking at neurobiology, who study how the brain reacts to different stresses. And of course, we're working on how humans interact with the environment and how the environment interacts with human beings reciprocally. But it's really interesting that we can organize across these different dimensions and find that there is some common ground. And we have some really interesting interdisciplinary research talks, and it's well beyond what we can talk about today. But I'm hoping we can have a dialogue with this department on an ongoing basis about some of the things that are going on within our building. And whoever wishes to come and get a tour of the building, it's a really interesting facility. It's got, in fact, all these laboratories that we can give you tours of. We have a beautiful auditorium. If you ever want to host an event, you can come up and do it at our institution. And there's a discovery center that reaches down into the public school system and brings students into our facility to learn about the science that we're doing. It's a really innovative and interesting kind of museum-like environment within that building itself. Okay, so with that introduction, let me begin by talking a little bit about ecosystem services. And back in 1973, and I've rediscovered this paper a few years back, and it was a paper by a guy named Howard Odum, who was really a leader in the field of ecology for many years, and he really brought ecological energetics to a crescendo that he then used to jump over into the world of economics. And he was really quite a clever thinker, and he wrote this paper back in 1973 where he was just conceiving of the role of the biosphere in supporting humankind and supporting our economic system. And since that time, the world of environmental economics has really taken off. He's, I think, in some sense, the founding father of that, or at least in my view, he is. And as a young guy, and I'm going to do something probably that I like to say is probably the bravest thing that anyone could do in an academic world. I will show you how an impressionable guy who grew up in New York City viewed this kind of stuff. And just a lesson to be learned here is it took 50 years to grow this beard. We were talking about beards a few minutes ago. It took 50 years to grow this beard, and probably a few less years to get the thinner hair up top. But that's what happens when you become an academic. You change dramatically in the way you look. But anyway, what I'd like to do is I'd like to read these couple of important tenets, because the discussion that we're going to have following this is built on these, literally on these two statements, these assertions. So I'm going to read them so I don't lose any words here, but they're really critical, and that's why I'm going to read them. So he said that his tenet number 11 was, even in urban areas, more than half of the useful work on which our society is based comes from natural flows of sun, wind, waves, water, etc., that act through the broad areas of seas and landscape without monetary payment. An economy, to compete and survive, must maximize its use of these energies, not destroying their enormous free subsidies. The necessity of environmental inputs is often not realized until they are displaced. That was his 11th assertion. His 12th assertion, this kind of follows on from this, is that environmental technology, which duplicates the work available from the ecological sector, is an economic handicap. Okay, so I want you to kind of picture this in your mind as we go through the discussion. Okay, I also want to put this in more of a strategic global policy arena. Okay, and again, I'm hoping that most people know that back in 2015, 192 nations signed on to a what they call the 2030 Agenda for Sustainable Development. And from that agenda emerged these Sustainable Development Goals. There's 17 such goals. And although you could quickly take a look at this and pick out your favorite goal, for example, eradicating the direst forms of poverty, or eradicating hunger on the planet, or universal health, or protecting the biosphere, or climate action, or gender equality. They're all, in some sense, very, very important. But this hierarchical picture of what have often been looked at as egalitarian or equal force goals is put into, I think, a very important context for what we're going to be talking about. And that, namely, is that you might have aspirations for a vibrant economy, which is up top here, but you can't have a vibrant economy or a growing and sustainable economy without an appropriate society that has issues of equity and equality built in to the fabric of the system that then supports the economy. And in turn, you cannot have a functioning society or functioning economy without a functioning biosphere. And so the biosphere kind of is the foundation upon which these other aspirations, I guess there would be 13 above these 4 for the biosphere, these other 13 SDGs would not really be achievable without having a biosphere that itself is functioning. Okay, so this is kind of the mentality with which I think we can approach the more focused look on the water resource system. Okay, so just to focus in a bit on the strategic global initiative, the SDG, the Sustainable Development Goal for water, sits under something called clean water and sanitation. There are 6 sub-elements. Now, interesting side note is that I briefed the United Nations negotiators as they were developing this SDG. And it was really interesting to hear the debates going on, because the developing world scientists, the developing world negotiators recognized that their first order of business was to get clean drinking water and sanitation for their populations. To date, there are hundreds of millions of people who don't have clean drinking water, and about 2 billion people who don't have sanitation and hygiene. And they said, well, let's focus only on that. Through debate with members of the negotiating teams from the developed world, they indicated, and I think rightfully so, that you can't simply throw some engineering at the drinking water, the sanitation question. You have to really underpin sustainability with thinking about things like pollution control, better water use efficiency, integrated water resource management, and ecosystem protection and restoration along the lines of that previous diagram that I showed you. And again, parenthetically, one of the chief architects for this work was President János Adar of Hungary, who actually received a briefing on the climate question by experts, expert scientists at the Roosevelt House of Hunter College, I guess about a year and a half ago. Was that pre-COVID? I think it was pre-COVID, Bill. You'd have to correct me on that. But he received a briefing on some of the important scientific issues at the Roosevelt House. So there's a connection in some sense back to Hunter. Okay, so let's get back into the infrastructure question. And I want to make the point that the biosphere is important in a sector like water. And you cannot really think of sustainable development goal number 6 for water without really thinking about ecosystems. And there was a study that was published by a guy named Rob McDonald in the Proceedings of the National Academy of Sciences about 5 years now. And he looked at over 300 watersheds and drinking water systems for urban areas. Okay, and this is these are the sites that he is looking at. These are a couple of examples of the upstream contributing areas. It's just like we have up for New York City, the Catskills and the Hudson Valley contributing our water supply. So do these other cities. Okay, and what he did was he looked at a 100-year time series, or he constructed a 100-year time series of the condition of these watersheds that were feeding these urban water supplies. And you would anticipate that since these are serving millions and millions and millions of people, that they would be fairly well protected. But what Rob was able to show was these time series of these human incursions into these watersheds. And he tabulated the number of people, the density of people that were beginning to enter into these watersheds and the human activities that were associated there. He saw an incursion for over a 100-year period or 110-year period here of the growth of cropland, the growth of rangeland. And he also tabulated the associated levels of pollution for nitrogen, phosphorus, and sediments, all going up over that period of time. And again, think of this as an important part of the infrastructure system for urban water that is being degraded because of poor stewardship, because of poor environmental management. And that may be of academic interest, but it's also of quite important practical interest. What else he did was he actually assessed the fraction of those 300 treatment plants that had upstream watershed degradation from insignificant to slight to moderate and severe. And about half of these systems showed some at least moderate levels of degradation over that 105-year period that he looked at. Okay, and again, that's maybe of academic interest, but where this really becomes important is that he was able to document substantial increases in the cost to treat that water, both in terms of the capital and the operating and maintenance. So this is in some sense, a proof of concept for some of the things that I introduced earlier that Howard Odom was talking about in my earlier slide there. So just to be clear what we're talking about here, I show an example here of a couple of reservoirs that we can call gray infrastructure. That's the kind of the traditional engineering infrastructure. And it's in some sense, it's contrasted against the green infrastructure, but it's not really contrasted against it. It's really a system of green and gray infrastructure that supports this this reservoir, this dam, when it has potentially many uses as water supply, irrigation, flood control, etc. And for this kind of engineering to be efficient, it has to have these natural watersheds and uplands and aquatic ecosystems that feed into this system as being sound and of high integrity. Okay. Otherwise, this system doesn't really work. And the flip side, we show at the bottom here. We show an impaired gray system and how upstream degraded watersheds feed into this. Now, there are obviously reciprocal impacts. If you don't operate a reservoir correctly, you have all sorts of important impacts on ecosystems downstream. And I think John Waldman's part of the club here tonight, and he has written extensively about these kinds of questions. So we have green infrastructure, we have gray infrastructure, and there's kind of a third infrastructure. It's this human infrastructure. And the trip switch between whether you're in the upper half of this diagram or the lower half of this diagram really has to do with how people make decisions, how they value their ecosystems and their water resources, what institutions are in place, what technical capacity, what socioeconomics that you have. And this is kind of a very, very broad kind of pictorial overview of what we're really trying to say here. Okay. I mentioned President Otter. He was actually part of something called the World Bank High-Level Panel on Water. And he joined 10 other heads of state under the auspices of the World Bank and the United Nations to look at sustainable water issues, okay? And they had solicited inputs from the scientific community, and we were asked to produce a white paper on the use of gray and green infrastructure along the lines of what I just spoke about for the Sustainable Development Agenda. We wrote a paper about this, which was published recently in Eco-Hydrology and Hydrobiology. And it's summarized here diagrammatically. There's a lot to that white paper that we developed. There's a lot of policy issues, et cetera. But on top of it all, there was this basic concept, okay? So you have gray infrastructure and you have green infrastructure. And these are just some examples of what we're talking about. And on either of those two axes, you have low utilization of green infrastructure up to high utilization. And on the gray infrastructure scale here, you have the provision of insufficient services, some basic service, and then elevating at the top of the axis here, advanced service, okay? And these little balloon plots here show a 2015 vision of where a particular country might be, and 2030 was the aspiration, okay? And if I advance the slide here, we can talk about, for example, the example of Afghanistan, which has low green infrastructure and insufficient water services, and perhaps with some good thinking about using what green infrastructure they have and investing in the engineering to get at least some basic level of service, you would move from the A1 position in 2015 to A2 in 2030. Another example is Uganda, and sadly Uganda was in the news recently, but the point I'm trying to make here is that Uganda does have some very good green infrastructure that it can use to propel itself upward in this diagram towards a basic level of service that really honors the importance of the ecosystems in moving up the level of service in tandem with the engineering. New York City is shown here. We have a pretty decent amount of green infrastructure that we can use for our water supply, and we have advanced service, but we can become still greener, okay? We can protect more of that upland watershed, and Alan Fry is a great expert in this, and I'm sure he could elaborate further. The whole trick here is to try to get to this upper right corner where we believe there's going to be great cost savings. There's going to be the valuation of ecosystem services that's going to help you get a running start on your water security. And so we kind of posited that as a framework. And now in the current work, we actually have begun to evaluate this in very concrete geographical terms, and we start to put economic numbers on these trajectories. Okay, I crank back the hands of time a little bit here. So this is a vision that we generated in terms of the threats to water systems in a paper that we published in Nature back in 2010. This is around the turn of the century. And as a consequence of development, as a consequence of poor land and watershed management, or of pollution, or of poor water management and overuse of water in many parts of the world, and also biotic stresses on the system, we produced a picture of what we term a global syndrome of threats to the inland water resource supply systems that give us our water, okay? And wherever you see red, it's a high level of threat. Wherever you see yellow or green, it's intermediate. Wherever you see blue, it's a relatively low threat, okay? A higher quality water systems. And what you see here is something a bit surprising to us. If you look at a place like China, for example, you would expect China, or India for that matter, for those of you who have visited, that the water systems there, the water resource systems are under enormous stress. And they get red colors, as you might expect. But we also see that the ambient water resource condition out there in the wild, okay, from which we draw our sustenance as users of water. If you look at Europe and if you look at the United States, you see red. And initially, we could not believe that this was coming up. But in point of fact, if you look at the literature, you see that there is, in fact, high levels of impairment in these two countries, in these two regions, in regions that have a high level of technical capacity, regulatory oversight, and should know better. But what we discovered is that there's this background level of threat that then, as you will see in the next couple of slides, is remediated so that we can deliver it to the human users. Okay, so this is what we see out there in nature because of humans impairing the system. And then we try to fix that system at the point of service so that we can turn on our faucets and get clean and reliable water supplies. Okay? Okay, so here's the conceptualization of what I'm talking about. So what we've done here is we've produced 3 maps that I hope to explain hopefully quite simply, and I think they're intuitive. This is the water provisioning service to humankind in volumetric terms, okay? And what this does is it takes a hydrologic estimate of how much water there is, and it matches it to how many people live downstream of that water. So it's a combination of a geophysical data set and a social science data set, which in this case is populations served by upstream water supply, okay? If you can follow that, you would see a place like the Amazon, which is the world's largest river system, which contributes 10 to 15% of all the runoff on planet Earth. That shows up as a very light color of blue, as opposed to places that are that you can find watersheds in India or China that, just by way of the fact they're serving huge numbers of people, they get very dark coloration. So this map here is of the downstream population served by the upstream source areas, okay? But the coloration here is important. It's blue, okay? Now, if you were to come into the picture, monitoring what is the state of affairs in the background from which we draw our water supplies, you'd see a lot of red here, similar to the diagram I showed you in the last slide. And this is the exposure of people to different source area threats. So it's this diagram with threats superimposed on top of it. You see now a lot of red. As I mentioned, humans, as a consequence of developing, don't seem to be good stewards of the ecosystem. So what do? What we do is we throw lots of money in terms of engineering at trying to recoup as much blue as we can. And if you're a rich country or a rich region, you can do a pretty good job of it. Look at the United States, look at Europe, right? Whoops, I meant to just stay on this slide for a second. And we're in a good position because we can afford to throw engineering at remediation, okay? But lots of the rest of the planet cannot do that because they cannot afford to do this. So all of a sudden, you have this major strategic social division between the haves and the have-nots. Now,
hey, Charlie?
Yes, please.
Quick, a clarifying question has come up.
Yes.
So for, I assume that we're talking $0.7 trillion,
Yes.
correct? And what time frame are we talking? Is this current dollars?
Yeah, that's an annual. I should have written that. Thank you very much. That's an annual
expenditure
inflow of revenues into the water sector, which is an engineering sector, essentially. Yes, it's $0.7 trillion per year to repair the damage, so to speak. Okay, and make the water ready for human use. Okay, now. This is predominantly engineering, as the diagram here says. Now, in the backdrop, in a very Odom-esque-like way, the ecosystems are working their magic, okay? And we have made some calculations that indicate that if you did not have the ecosystems quietly working their magic, if you took away all those ecosystem services, you would see a world with not just red, but black, which are really, really high levels of threat. And we've begun to put numbers, and I'll explain this as we go along, we've begun to put numbers on this. And by our best estimates, it's about twice as much value in those ecosystem services than what you spend repairing the damage through engineering. And if you were to remove those ecosystems, the bill at the end of that meal is going to be 1.4 trillion versus 0.7 trillion today. So we'd be spending over $2 trillion to clean up the water systems. And even when doing so, we wouldn't do this universally, okay? So I want you to keep this in mind. So the ecosystems are working quietly in the background. The observed threat is, despite what they've been doing to dampen the otherwise higher levels of threat. And then we remediate that through engineering, okay? And we'll go over these numbers as I go through. Now, let's get back to the SDG, the Sustainable Development Goals. One of the Sustainable Development Goals is the eradication of poverty, okay? And if you look at estimates of where and how we're going to be developing economically. One of the major thrusts and one of the major anticipated success stories is the rise of the global middle class. And the global middle class, as distributed across a income axis here, and these are the number of people in each of these categories, you see this bulge at around, I don't know, maybe around $1,000 to $5,000 per year. That's the global middle class of year 2000. By the year 2030, it's moved up the scale, the wealth scale, and by 2050, it's moved still farther to the right. Absolutely one of the fundamental objectives of the development agenda, and it seems as though this may very well happen with economic development. Now, that's all well and good, but by our best reckoning, and you'd have to read the paper that we wrote to look at all of the reasoning behind it, but by and large, what we find is that with such economic development, you're going to have more threat to the water systems. And this is a map that we produced for the year 2050. These are regional increases in the threats, okay? Globally, going up about 7 to 8%, with hotspots for places like India and China, okay? That's somewhat intuitive, but it's also somewhat sobering, because while SDG number 1 might be attained if we do business as usual, and that is as we have in the past, and focusing mainly on impairing the system and then repairing it with engineering, we're going to see this in terms of the background level of threat to our water resource systems. Okay, so it's an I would call it an orthogonality in the SDG agenda. Okay, now you saw a really, really big number, double the value of these ecosystem services versus what engineering we throw into the hopper today. Okay, and this arises from the fact that the replacement costs for if you had lost the ecosystem service and you had to replace it with engineering, is on average about twice the cost of each unit of engineering de novo from the start, right? It's the reparation costs, if you will. And the function that we have used is representative of how environmental economists would look at the role of the environment. And in kind of green space here, the better conditions show you an engineering threat reduction that is quite low, where you have good environmental conditions and where you've lost the green infrastructure with poor environmental conditions. Your per unit cost in terms of what you've lost from nature and you've got to replace from engineering goes sky high. And that's why even as we develop the Earth, and we're going to be losing more and more of the natural planet, the costs of doing business go up. And that's why we see it's extremely important to preserve the environmental services, okay? And these two maps here are showing how we anticipate the future to unfold. And the bars down here at the bottom are, they range from blue down to brown, I guess in my color bars perception. And this goes above 300% to down 100%, okay? And for many parts of the world, we are going to see multifold increases in the traditionally engineered solutions and investments in those solutions for our water security, if business as usual trends hold. And places like Africa, which have very little such infrastructure today, or it's in great disrepair, are going to see multifold increases as they economically develop. Okay, that's kind of intuitive because, you know, you'd see less of an increase in a place like the United States or Europe because we have that kind of engineering. So we're not going to create a multifold increase, but they will in places where the development has been restricted, okay, or limited. Now, on the bottom, this is the engineering. On the bottom is that green infrastructure, okay, that natural capital, as we call it. And by and large, as you see a lot of expansion here, you see a lot of contraction here, that there's a lot of loss of these ecosystem services. Why is that? It's because with development, we have seen an increase in the human footprint and a whittling away, some might think that's too kind a word, but a degradation, a progressive degradation of the environment. And that's what we're picking up here. So at the same time, the engineering is blossoming, we're also finding that the ecosystem infrastructure is being depleted. Okay, so what does this mean? In the period of the SDGs, this is the middle of this 2050 period, we see about a doubling in the growth of the water sector from engineering, okay? Now, at the same time, we're losing this natural capital. But as that last graphic, that exponentially decreasing graphic, or increasing as you lose the natural capital, shows, the value of the ecosystems are going to exceed the value of the engineering, even though we are losing that natural capital. And it's because every unit of natural capital you lose sequentially it becomes ever more expensive to replace it with the engineering, okay? And now we're talking some quite substantial amounts of money. And we're also talking about the fact that ecosystem services are on par with the traditionally engineered expenditures that we make. Okay, what's the path forward? Okay, I grew up in New York City. I grew up in the Bronx. I'm allowed to consult our veteran philosopher on such matters, and that's Yogi Berra. And if you know anything about Yogi Berra, he had some funny sayings. Okay, one of the sayings that he had was, "If you come to a fork in the road, take it." Okay, so how does this relate to what I'm saying? Like this. So what we discovered when we put all of this information together is that you can organize yourself around these couple of axes, again, engineering and green assets. And you can document where we are today with respect to how much engineering and how much green infrastructure you have. Okay, so wherever you would, let's just take South America here. Wherever you would see blue color, you have relatively low engineered assets, and this is a globally relatively low engineering assets, but you have high green assets, okay? If you look at a place like India or China, you see a lot of yellows or yellow and browns, and these colors are shaded here, but by and large, you're in this B section, okay? You have low levels of engineering. You have a lot of water security you still have to execute using engineering, but you have very low green assets, okay? Well, then the question is, how can you move into the future? What's the choice here? And those who have lots of juicy green infrastructure like South America can go up to this top right corner, which we talked about earlier, and you've got high levels of engineering, water-based security, and you also have a lot of green assets that you can throw at the challenge. And in fact, you can see places in southeastern Brazil, as a perfect example, have very, very high levels potentially in the future of water security from engineering, but also water security from green assets. Now, that's their choice. That's the Yogi Berra type choice that they could take. They could go in that direction. But if you're in a place like India or China, the coloration becomes dark red. The only way you can get to a high degree of water security is to engineer your way to that endpoint, because all of the decades of poor environmental stewardship have backed you into a corner. And there really is no other alternative. There is no choice. There is a choice if you have the green infrastructure, but if you don't have the green infrastructure, you may very likely have to afford and realize the water security purely through this gray engineering, okay? And that's a very, very important point as we move into the future, because again, if you're in this bottom situation, you're paying way more per unit of water security than if you're going in this particular direction. Okay, so I showed these graphics before, and we analyzed a little bit what this really means in terms of the development agenda, okay? And we produced something that we call our Sputnik diagrams here. And what we're looking at here is on the top, the traditional engineering approach, looking from the year 2005 to 2050. And what we did in the top diagram here is we ranked the countries, which are each of these dots here, from, I guess we did about 150 countries down to number 1, in terms of their investments in traditional engineering for year 2005 and then upcoming in year 2050. And as I mentioned, places like Africa, you're going to see a very, very dramatic increase in the amount of engineering infrastructure. And therefore, the rank may actually change based on the status quo of 2005. And we express this as a set of colors. We took something called the Global Innovation Index, which is kind of a composite index of how ready a society is to execute its technologies, to develop an economy, to innovate on social issues, to educate its populations, but it's a composite index. And wherever you see purple here, that's level 1, that's a high level of innovation versus a low level of innovation, okay? And what we see here is that these countries, this is the one-to-one line here, what you see here is these countries that are in these lower quartiles relative to 2005 are bouncing above that one-to-one curve. So their rank in terms of their investments in traditional engineering are bouncing up. And think about that for a second, though. These are where all those investments are going to be made in traditional engineering, but these are the very places that have the least technical capacity to really accommodate these pieces of engineering. And just as an example, in Africa, the World Bank assessed African infrastructure, including for the water sector, and they found that about 30% of African water infrastructure was in severe disrepair because they simply don't have the technical wherewithal or the economic capacity to keep these systems going. So just where we see these investments being made, it's in precisely the places that are probably least likely to be able to make best use of them. Similarly, if we look at the replacement costs of natural capital, and again, this is that loss from 2000 to 2050 here. If we look at the rankings here, we find that these systems that are colored in the pink and the orange are thrust above the one-to-one line, okay, indicating that those are the same countries with very low innovation capacity that have to cope with the lost natural capital. Okay, this is the replacement cost for the natural capital. So they get that double hit. They're getting the traditional engineering that may be maladaptive to their setting, and they're on top of it having to accommodate the lost natural capital. And as I mentioned to you earlier, that's very expensive. So they're getting hit twice. Lots of engineering that just costs money to install. And then on top of it, it's going to have this additional struggle from the loss of natural capital. Okay. All right. So that's basically the core of my talk on the green-gray infrastructure. But I thought, since this is a geography department, I'll share with you just a couple of musings that I would love to come back and talk to you all about at some later point. But I kind of structured this as the grand challenges in water, okay, that are geographical in nature, okay? And one of the big issues that I still think the community struggles with is how do we articulate the connection between social dynamics or social dimensions and the hydrology. And let me show you why this is important. This is a bit dated. This is from a paper we wrote back about 20 years ago, where we did a very, very simple thing. And we did a simple thing because we were nagged by what the United Nations was doing, okay? And the United Nations at the time was expressing water security issues and water struggles as national imperatives, okay, that really didn't appreciate the geography of the inherent system. You know, in the United States, they were saying that we have sort of a moderate level of water stress as articulated by a ratio of what you're using to what you have. That's what this ratio is about here. And if you have dark blue, you're water rich. If you have light blue, you know, you're okay. But if you start getting to pink and red, it becomes more dire. And of course, a place like the Middle East shows up dark red, as you would expect. But a place like the United States, with Alaska tacked on for good measure, has one color. And we know, just driving across the US or looking out a plane window, that's absolutely not the case. There are all sorts of gradients, both in terms of the water availability and also how water is being used. And so just from a very intuitive geographical perspective, we tried to capture the distribution of water supply, and we tried to capture the distribution of water use. And then what we did is we tried to reconstruct this diagram that the UN was always using. And we came up with something that looks like this, where there's lots of red and lots of blue, and these are densities of population. And it's a very complicated picture. But of what practical value this has is, at the time, the United Nations, this is the end of the 1990s, the United Nations was declaring about 500 million people were suffering from severe water shortage, water stress. And we could come up with the identical number at the national scale. That's what these two numbers are here. So we were looking at high levels of water stress. We got the same numbers at the national scale. But if you disaggregated like this, we more than tripled the number of people under severe water stress. And at the time we were developing these geographic numbers, we were really scared to put this out there, because this completely changed the way people looked at these numbers. Well, we did. We actually published this, and as it turned out, people tested what we did. And what they found was that our numbers, 1.76 billion people under severe water stress, was probably an underestimate. We were actually conservative. And so just some simple, I really want to say, as geographers, you should love this, just some simple geography really re-articulated the whole global pattern there. So anyway, I just wanted to show that one example. There are many other examples that I'd love to come back and talk to the group, or members of my team could talk to people in this department. Positioning water infrastructure and its condition. It's really interesting. I worked with some people looking at African green and gray infrastructure, and we discovered that we could actually make some pretty good estimates of where there was good, juicy green infrastructure that could be used for water security in Africa, because of decades of land cover change monitoring through remote sensing and in situ of validation of those data sets, et cetera. When we tried to assemble engineered water infrastructure data sets, we found that it was extremely fragmentary. It was listed by country. It was listed in different ways by different countries. It was a mishmash of chaotic reporting. And that I view as a grand challenge, because if what we're saying is true, that engineering has to work with green infrastructure, if you don't know where the engineered infrastructure is, and you don't know its functionality and its condition, we're going to be struggling with this for years. There's also a geographic issue having to do with a domain of sustainability investing, and there's evidently trillions of dollars sitting in bank accounts that could be invested in businesses and products and services that do good, that will help with the climate question, that will help with human health, that will help with equity issues, that will protect the environment, etc. And there are companies that are claiming to be producing those kinds of products. For example, water companies that produce pumps that go into wastewater treatment plants. And that's all well and good. And they could claim that they're helping the sustainable agenda. But one of the geographies that's missing is, where are these products winding up, and where are they doing good? Where do all these pumps that presumably will be cleaning receiving waters, where do they wind up? It's very, very inexact, if unknowable information at the moment. And again, that's a big grand challenge for geography. Also, in terms of positioning, you can look at this more broadly. Where could you invest in protecting green infrastructure, installing gray infrastructure for water security? Where could you do this? How would you calculate that? We're writing a paper right now to look at some ways to do that, but it's not really a science yet. It's a bit of art. Where could the public sector or the multilateral banks or the private sector come in and help with water security needs? That's a difficult thing to map. Where would the beneficiary populations be located? So it's one thing to say, well, we're going to do good, we're going to put in all of this infrastructure, but does it make utilitarian sense from a population standpoint? That can be imminently mapped, but these other 2 points, you know, where you could invest and who actually pays for it, completely open questions, but it's a geography question. Getting back to a little bit more of the technical aspects of hydrology, we have been analyzing river networks throughout the work that I've been showing you. And it's interesting because climate signatures come from the sky in some sense, but hydrologic signatures and water shortages often go through river networks and groundwaters, and they are in some sense reconfigured, some might say distorted. A good example of this would be to imagine the Nile River, okay? And the Nile River in its uplands has the waters that flow ultimately into the Mediterranean Sea. But it flows through super dry areas, and it's also in the originating source areas are undergoing extreme climate change. But the climate change is playing itself out as a change to river flow and change to groundwater recharge, etc. How this all plays out, I think, is a major technical challenge. And then finally, a lot of what I've shown you today in terms of the maps, etc., was really made possible by huge investments that that have been made by governments of the world in terms of the research infrastructure, in particular, how remote sensing information and large-scale integrative models and data processing systems could really begin to synthesize this information. We've done a small part of that synthesis in what I've shown you today, but really we couldn't have been even talking in these terms. And I could say that over my career, we couldn't have, at the beginning of my career, we certainly, without my beard, we couldn't have been talking about this. Now we can talk about this, decades later. And that's a real advancement, and it's very geographical in its nature. And it's I think it's many low-hanging fruits that we could all work together on as Earth System scientists and geographers to really take best advantage of. So anyway, that's the end of the discussion. I could take my discussion. I hope we can take some questions here. And there are some links. If you Google CUNY ASRC ESI publications, you'll find the papers that I've spoken about today. So thanks for your attention. I hope I didn't run over too much, but I get excited about this stuff and I sometimes get carried away. So, but hopefully we'll have some time for some questions. Thank you.
Great, Charlie. Thanks so much. I think Andy's going to continue picking up some of the Q&A, and I think just as a start, really congratulate you on a absolutely brilliant and sweeping presentation of such a critical issue. So thanks again. But to Andy to help moderate some of the questions.
Great. Thanks so much, Charlie. This was wonderful. I've heard a similar talk a couple of times, and each time I get even more out of it. So it's been great. So let's see. Anyone have any questions? Feel free to raise your hand and we can call on you, or type it into the chat window and I can read it. Alan.
Thanks, Andy. First of all, Charlie, just thank you for presenting that kind of viewpoint. It's just it's really moving to me, to hear you present that kind of global and interdisciplinary viewpoint. It's very difficult. I don't know if everybody realizes how difficult it is to do what you're doing. But my question is, what about, in the last, the US went through this dam building stage in the 20th century. China has done that in the last few decades. And so, they're moving water over very, very large distances from one place to another. Now we've got I would characterize it maybe as still fledgling industry of removing our dams, right?
Mm-hmm.
So how do these changes over these decades, how do these things, are they big enough to have an effect on what you're talking about here? Or, isn't that part of it?
Yeah, well, absolutely. So probably one of the easiest things to, and it's all in relative terms, it's a difficult process. One of the easiest things to map out are the dams and reservoirs, because you could see them on planet Earth. I mean, they're not buried. They're apparent. When we first analyzed the impact of reservoir systems, we actually, this is back in 1997, we published this. We actually had to rely on operational navigation chart maps. Okay, I don't know if you all know what that is. Back in the pre-internet and pre-satellite GPS days, pilots used to take maps that were 3 feet by 4 feet long with great resolution on a paper map to show the surface of the Earth, okay? And on those maps, they had all sorts of attributes, like where the cities were, where roads were, and where reservoirs were. So what we did is we literally digitized these maps. And when I say digitized, we looked at the maps and we picked up where a reservoir was, and then we manually entered it into our database. Extremely time consuming. I think it took, to get 600 dams and reservoirs, it took at least a year for us to do this. In the interim time period, of course, with Google Earth and Earth Engine and all, and artificial intelligence and such, there now have been mapped tens of thousands of these things because they're apparent on the land surface. And we can map these things out. And so we can see that they were there the whole time, but we never really recognized their importance. And we made some calculations, and a lot of these occult, I would call them occult engineering works that you couldn't see earlier. We didn't know were out there until, satellites would inventory them, etc. We found that they have an enormous impact on things like sediment flux to the ocean, and about 1/3 of all global sediment doesn't get to the ocean anymore. And if you happen to live on a delta that doesn't get nourished by those sediments, you're sinking very, very rapidly. You also have all sorts of coastal erosion because of this. This is a major geophysical impact of these engineering works, right? That in some sense, we didn't know their full impact until quite recently. So, notwithstanding the removal of dams, which I realize is important for, biotic purposes, for protecting ecosystems, there is still a lot of dam building. And I've seen projections where the same rapid increase that we saw when we developed is going to overtake much of the developing world, with severe impacts on the biodiversity, particularly because John Waldman can speak to this, the biodiversity in aquatic ecosystem, freshwater aquatic systems is quite endemic. There's a lot of intense speciation that's particular to individual river courses or river basins. And if you're a fish and something happens to your water system, either the dams or reservoirs are releasing water in an odd way and thermally shocking you, or trapping sediment, or depleting the water supply if you use the water for irrigation, you have no escape. You can't just jump out of the water and watch it go downstream. You're there and you get hit by it. And the levels of species loss are orders of magnitude higher per unit area in these aquatic ecosystems than for the ocean or than for the landmass at large. So I think that dam building, there's an imperative to develop just like we did, and people like John Waldman are attempting to create alternatives to that dam building. But I think that's a force to be reckoned with. Let's just put it that way. It's going to be part of the hydrology of the planet. In fact, I kind of argued earlier whether we should be really thinking of global hydrology as global hydrology or global hydraulics, because a lot of this stuff is just human controlled. It's no longer free flowing in lots of parts of the world. So, and anyway, I'd like to hear what John has to say about that. But I think that's where we are in the future, Alan. Unfortunately, or fortunately, it depends what your perspective is, right?
So we have a lot of questions trickling in. I think Mariana was next, but real quick, just to get everyone up to speed, there was a good kind of fundamental question here. And the question is, what is loss of natural capital? And unfortunately, as you go to answer that question, I'm going to transition to having Bill take over the Q&A because I have to run and give another talk in a few minutes.
Yeah, that's okay. That's how the ARC folks work. One person stops talking, the other one starts talking. It's just how they generate that way.
Okay.
So Charlie, maybe just define very quickly natural capital, and then there's a series of other questions coming in.
A very good basic question. So I'm going to go back to that diagram if I can find it here. Let me go back to this diagram. Oh, can you hear me?
We can hear you good. Yep.
Okay. I'm going to go back to this diagram. So natural capital is this so-called green infrastructure. Yeah, the nomenclature, it is a good question because the nomenclature is not so clear. And so people talk about natural capital. People talk about nature-based assets. People talk about green infrastructure. And people talk about ecosystem services. And there's a little bit of definitional blending, let's just say, but pictorially, just this is the green infrastructure that we're talking about. And these systems were meant, and I'll just increase the screen here. These systems were meant to be indicative, these photographs of intact ecosystems, okay? Well-functioning forests, clean water supplies. They attenuate extreme floods. They maintain groundwater flows, etc. Okay, clean and well-functioning aquatic ecosystems support life, support fisheries that humans might draw protein from, which is an important food source in many parts of the world. The loss of natural capital is captured by these diagrams down here. So we have degraded landscapes, okay, where you go in and you cut all the forest down, you don't bother to replant it. And whatever comes back, and there's lots of erosion, there's lots of change in the amount of water that flows off of these systems, often flooding downriver places, including some cities. And these pictures just are attempting to show what these healthy systems look like when you degrade them. That's merely what we're trying to say. And I hope that answered the question. I hope it did.
Yeah, I think it provided lots of detail.
Okay.
Thanks. So Mariana has a question coming up next. If you want to drop out of screen share, please. Yep. Mariana.
Yeah, thank you, Charlie, very much. That was very interesting, and I do appreciate this kind of global perspective on those issues. So I have two quick questions. One is that, so what kind of data are you using? At the end of your lecture, you gave credit to different governments producing data that is possible to use in your research. So, so you take the data, you do modeling. Like, I'm just wondering, how do you come up with those maps? How do you come up with those estimates? Yeah. This is one question. And the second one is, in terms of this kind of development trajectories that you outlined, you kind of said that the countries that are rich and have a lot of great infrastructure actually do damage the green infrastructure in very, very substantial ways. They do have an advantage of having more capital to repair it. But the point is that the development trajectory on which we are finding ourselves is damaging the green infrastructure. And so then you have this kind of predicament for the countries that still have some of the green infrastructure. And the big question is, should they follow the same path and find themselves in the same kind of conundrum, but without financial resources because they don't have them as a result of this kind of global colonial system and all this kind of stuff. So thank you.
Yeah.
Charlie, if I could just
sure.
bundle another question that came in from the chat from some students in one of the classes that was viewing. It's very similar, like, you know, given the vice, so to speak, that sub-Saharan countries are in, like, what choices can you make in investment, in terms of investment, which I think mirrors, Mariana, your point a little bit as well.
Yeah, those are linked questions. That's exactly the case. Again, I go back to Yogi Berra, okay? If you come to a fork in the road, take it. Well, of course, that doesn't say anything. So we do have a decision point. And if what you believe out of the discussion is true, namely that as you destroy the green stuff, you pay a premium. You pay about twice as much for each unit that you lost if you've got to replace it with engineering. It means that every time you sail down the engineering path, and each time you have business as usual with respect to the loss of natural capital, it becomes increasingly expensive to execute water security. Okay, so that's the logic here. So part of the whole puzzle here is to stop the environmental degradation in the first place. And when you can, use it to your best advantage. By simply stopping the degradation, you get a bonus, you get a benefit, because you are not progressively increasing the price tag for the water security. Now, one thing that we did not do is we did not evaluate what it would cost to rehabilitate the system. So first thing is stop the environmental degradation and use the green infrastructure to your benefit. It's got free services, just like Howard Odom said, right? It's exactly what he said. And that's the first step. The second step is those damaged ecosystems, you will have to invest to fix them. So a place like India or China that has had a long history of degradation and loss of green, they would have to reconstitute the green infrastructure. They're going to have to pay for that. We didn't look at that. That could be radically larger than the containment cost, or I should say the protection costs. We haven't done that, but there's evidence to show that that might be very expensive. The good news, however, is that people who study ecosystem restoration can understand that you don't have to rehabilitate the entire domain. You can target it to different regions within the landscape. For example, the land that is adjacent to a river does quite a bit of good with respect to protecting water quality. And those so-called riparian zones can be targeted for remediation. But you ask a really fundamental question. And the first step, I think, is just to stop the environmental degradation. There's a benefit from doing that. But it's going to cost us to rehabilitate and get the full benefit. I don't know what those numbers are, Mariana. I have no idea.
Right. Well, thank you, Charlie. But I also think like the issue has to be bigger. Like we have to rethink the way we develop, because it seems like so far it hasn't really deliberate, right? Neither to humanity in a big way, but also it's damaging to the very foundation of our life, to those green infrastructures that you described today in this topic.
Yeah,
So
exactly.
that seems like very, very important issue.
Your first question, though, I wanted not to forget your first question. Your first question was an interesting one from how do we actually get this done? So one of the things that we had to do was we had to assemble a series of stressor maps that produce those threat indexes that I showed you. And there were 23 of them that we were able to bring together. When we originally conceived of this idea, we thought that it would take us 6 months. It would take us about 6 months to get the data sets together and make the calculations, etc. As it turned out, it took about 2.5 years. And the reason was that we were taking existing data sets for climate, existing data sets, for example, nitrogen deposition, existing data sets for where the dams and reservoirs were, et cetera, et cetera, et cetera. Those data sets, although they were global, were created for completely different purposes. So what we had to do is we had to repurpose these data sets. We had to harmonize them. One of, I guess it would be no surprise, one geographical stumbling block for us was that a lot of these data sets failed to have a common coastline. So what we had to wind up doing was we had to figure out, well, if one grid cell, and these were digitized grid cell based maps, one grid cell had an ocean grid and another had a land grid, how would we reconcile the two? If we had people living in the ocean because one data set didn't use the appropriate resolution coastline, we had to figure out where to put those people. So it was an extremely GIS intensive.
Exactly.
It wasn't the modeling, it was the data preparation. And we had a dozen or so people looking at each of the data sets, and they were each experts in different realms. And people who were doing some of the the work on acidification and such were able to help us interpret the maps in a very different way. But that was the time-consuming issue. It was not the modeling, it was the data prep. But they were out there, Mariana, but they were produced for very different purposes altogether. So
thank you very much.
Great. So we have 2 more hands up and then 1 more question in the chat. So I think Mohammed, you're up next.
Oh, thank you, Bill. Thank you, Charlie. It is very interesting talk. In one of your slides, you said that there is the rapid loss of green acids, and you have talked about how there is an increased investment in engineering. If we push it a little bit further, that is a big environmental problem, because if we can think comprehensively, the future, the green future cities and sustainable cities depend on that green, which is diminishing. And at the same time, the increase of population, and at the same time, the challenge of sustainable climatic change, all of these are coming together. So thank you, you have dealt with engineering. Have you ever think of the human dimension on restating back the green loss? That's my question.
If I get the nature of your question, I'm going to answer in a slightly different way, but I think it's appropriate. One of the things, well, first of all, getting back to Mariana's question, we used existing data sets, okay? So we used existing IPCC development scenarios, the SSPs, okay? We looked at a series of them. One of the things that we noted was that it was very difficult to find off-the-shelf scenarios that showed anything but economic growth, okay? And we took them off the shelf, okay? Now, I've had some discussions since we started this work, and there is now, I believe, a growing community that's going to be talking now ultimately of economic stasis, if not contraction. And they go back to actually a book by Howard Odum called A Prosperous Way Down. And he, before he died, he collected all of his thoughts and he put it into a book where he speaks about how we're going to go through a transition after the transition of cheap fossil fuels. And, there'll be renewables, etc. But at some point, we may not be able to continue growing the economy. And that's plausible. But most of the scenarios I've seen moves us up that curve. And as I said, SDG number 1 was to alleviate poverty. Global poverty means that there's going to be economic development as an imperative. That's boiled into the whole system. And to think otherwise, as we did, let's say in the early 1970s, has to be resurrected as a concept. And I think that there will be lots of intellectual battles over that idea. Just imagine throwing into the political domain the idea that we're not going to have GDP growth. Just imagine what would happen. That would be battled. You would be, you'd be shouted down, before you could get the words out of your mouth. So the way we think about growth of the economy is in essence part of the information sources that we tap. They reflect that mentality in the information sources that we use. But yes, I've thought about this. I didn't want to go off on my own. I wanted to use some bona fide peer-reviewed trajectories. And perhaps there is, with this new group, these groups of people that are now talking about zero growth or contracted growth. And people now are also talking about, population contraction, which used to be something we could talk about sensibly, but now it gets really politicized and all. And I just am afraid that the human dimension of all of what we're talking about cannot be argued respectfully anymore. It gets so politicized and people get attacked and it gets polarized. But, if we're talking about planet Earth, and we're talking about one planet Earth, and we're talking about the future, what are we going to look like 200 or 300 years from now if we continue doing what we're doing? And, there have been some estimates that, there are 2.8 planets that would be required to satisfy the needs of the growing population in the future. I don't, or if not now, I don't think it is sustainable. We have to be thinking, what happens next? Yeah. It's a great question. It's a super great question.
Hey, Charlie, actually, I think our next question by Ramiro Campos is going to throw some more fuel on the fire of discussion. But it's okay to segue, Mohammed, into this. Oh, you're on mute. You're on mute, Ramiro. Can't hear you.
Sorry, could you unmute?
No, I think he's having headset issues.
Oh, a headset issue.
Okay, I think I got it now.
Yeah.
So you more or less answered the question, a series of questions that I had, and with that answer, it was very similar to what Dr. Ibrahim was gonna what he asked, but I had more questions about the articulation of these social hydrolinkages, and basically answered it because where are the data sets on what does sacredness mean? Right, like sacred rivers like the Yamuna, or what happened at Standing Rock, and how this affects, how development is going to impact the social sphere. But I was wondering what the role, and my understanding of the presentation was, if we continue as business as usual, is going to cost you more to do this. We have to look at alternatives, and to what degree are those alternatives? So does the data set look at not just deforestation, but industrial agriculture, and looking at alternatives such as afforestation, like the Great Green Wall, right, in the Sahara, and the Great Green Wall in China? How do they look at that as a form of green engineering, or is this strictly right now with the, so how are those projects going to be studied in the future?
And if I could add one other question onto that pile, Charlie, we had a question in the chat about places like Newark and Detroit or LA are trying to do things, you know, they recognize, but I know you've also looked small scale, like, because we've talked global, but also small scale, which is embedded in the conversation. You know, these places that have aging infrastructure and, you know, crumbling infrastructure, while they also have, like, you know, reduced financial capital and accessibility to money, although the infrastructure bill is now present, like, how can they sort of affect change even when the political process is so mired in sort of short-term, you know, decisions? And rather, we've started a conversation looking at the arc of change over time, I guess what I'm trying to get to, and how do we sort of, you know, get into that space when so many things are, you know, are embedded in the here and now?
Yeah, I think you're talking, you know, what is the call to action? What is the scale of the call to action? You know, yeah, we think globally, we act locally, but we also have to act globally. I mean, the climate question is a global question. The water question, as I have argued in the past, has lagged behind the climate question with respect to action. And I stated very much in passing, I give a lecture on this, but very much in passing, there are about 2 billion, if not more, 2 billion people who don't have access to sanitation services, to human waste disposal, okay? About 900, maybe 850 million people don't have access to clean drinking water, right? Now, that's, I think, you know, if everyone believes that water is a human right, that is certainly a violation of a human right, that people don't have the basics, okay? And that was the kernel of that argument that the developing world negotiators were making for the SDGs, that, look, you guys are talking from, you know, a platform of having all these services. It's great, keep thinking about the nature and the environment, but we don't even have clean drinking water, and we don't even have sanitation services. So they're just simply trying to serve the needs of the basic needs of their citizens, right? So the water question, in some sense, is quite local. So your interventions on water would be, for example, revitalizing aging infrastructure in a city, okay? Making sure that lead pipes are no longer lined with lead, that you would replace those pipes. Making sure that the dams and reservoirs are not going to collapse, okay? And those become, in some sense, very local problems. But they together across the planet create a global syndrome. And so the people who are suffering from lack of water security may appreciate the issue of global climate change control. They might appreciate that. But in many cases, they're suffering from the day-to-day affairs of poor management, okay? And so what I think we need to do is we need to search for win-win situations. So we need to be able to, for example, as I mentioned, begin to protect ecosystems that are disappearing, rehabilitate when you can. And, you know, those two things alone would be enormous job generators. And I guess there's in one of the infrastructure bills, I'm not sure which, there's a climate core. Maybe you know about this bill. There's a climate core to bring people into the fold of rehabilitating ecosystems, you know, and it's in part to help us with mitigating the extremes of climate, but it also would have this tandem benefit of protecting infrastructure. And I think the credo must be that if you screw up the environment, you not only lose the investments that you might have had in the environment and the services that it generates, you also have this collateral damage to the expensive built infrastructure. I've worked with some people down at the University of Virginia, and we look at the green-gray infrastructure issue in the watershed that feeds into the city of Baltimore. And because of the fact that they're not managing the green infrastructure as a lever, as a management lever, they get these intense floods in the downtown area. And then now they're trying to figure out, well, how do they do something to, make sure that there's more flood attenuation in the actual infrastructure in the city. But they're also thinking, well, we could probably invest upstream in the appropriate kinds of rehabilitation of those ecosystems so that the flooding won't be as intense in the future. So we have to think, I believe, in tandem. And your point is taken, the management of, for example, flooding in downtown Baltimore is going to be more of a local issue. It's not going to be an issue that's going to be tackled at COP26. But yet, lots of Baltimore flooding issues are happening all over the planet. So there's that shared imperative, but the management might take a very unique look and feel for Baltimore versus what it might for New York City, what it might for San Diego, California, et cetera.
Great. Well, I think that gives us throughout the evening, you've been sort of staying at the global scale, but sort of bringing it down to the local. So I'm really glad that we were able to sort of bring those threads back together toward the end of the presentation. And with that, I think I'll draw it to a close. I know it's been a long day already and a great presentation and a lot of Q&A. So thank you so much, Charlie, for joining us for Geography Awareness Week and sort of embedding your perspective deeply in the geographic discourse and sort of sharing your vision, really. So it's been a great pleasure. So I want to thank you all. There is another geography awareness event coming up tomorrow. There's information on the main geography department website that will illustrate that. I also want to thank Amy Ju, who's been behind the scenes helping out significantly. There she is. And thanks all. And Charlie, again, thanks. I don't know if we'll continue the conversation, as I know that you've been sort of really much engaged in this question of water. Thanks all. Thanks for everyone's attendance, and have a good evening. I don't know, Charlie, if you want to.
No, my pleasure. Simply, it was really wonderful to talk to people I think appreciated the geographic aspects. So that's really wonderful. Thanks. Thanks for that.
Excellent.
Appreciate it.
Okay.
Thanks.
Great. Thanks all. Take care. Be well.